Rising within the urban landscape, this is designed to balance comfort, functionality, and modern living. Thoughtfully planned spaces, efficient design, and strong connection to the community come together to create a home that supports everyday life while shaping the city's future. We would like to welcome you to Lux Vivere Residences, a mid-rise residential project. This project is served by our team composing of Project Lead and Lead Architect Michael John Landoy, Structural Analyst for Gravity Loads Rhea Angelica Mundayan, Structural Analyst for Lateral Loads Jesseline May Nimo, BIM and Rebar Detailer Cristel Hevero, and I am your Technical Editor and Narrator Rain Madel Trovela. Lux Vivere is designed to enlighten contemporary living conditions through thoughtful integration of light, space, and human-centered design. Derived from the Latin words lux and vivere, the project embodies the philosophy of living through light, where natural illumination becomes a fundamental element in shaping comfort, well-being, and quality of life. The concept emphasizes strategic use of natural light, influencing building orientation, massing, facade articulation, and spatial organization. It integrates architectural, structural, and environmental strategies to create a building that is efficient, adaptable, and responsive to its users. By maximizing daylight penetration and visual openness, Lux Vivere creates healthier living environments that reduce reliance on artificial lighting while enhancing residents' physical and physiological comfort. Thus, it considers natural lighting, flexibility of spaces, natural ventilation, and structural integrity. Main materials used for this project are concrete, wood, breeze blocks, and tiles. To further discuss the structure, let's start with a 3D exploded view of concrete frames and dissected floors to see the layout of the rooms better. Framing plans define the column grid, beam plans, and slab systems, ensuring structural efficiency while supporting open and flexible residential layouts. Two-way slab systems are strategically selected to balance material economy, span requirements, and spatial openness. A load path analysis illustrates how structural forces travel through the building. A point load applied at the roof level is traced visually as it transfers through slabs, beams, columns, and finally into the footings. This process ensures that loads are safely and efficiently carried to the ground without compromising architectural intent. By aligning the structural grid with the building's open layouts and breeze block corridors, the schematic phase supports both performance and design clarity. First, let's have the dead load for the roof. For the slab, we only have one type of slab with a thickness of 150 mm, that is stone concrete fill. And as per the table 204.2 of NSCP, for stone concrete fill, it has 0.023 kPa. We will multiply it to the thickness of the slab and the answer will be 3.45 kPa. Next is acoustic fiberboard as ceiling. Based on NSCP, it has 0.05 kPa. Lastly is the electrical and plumbing materials, which is only assumed as it can have 0.3 kPa. The total will be 3.8 kPa for roof only. Next is the beam. It has 300 by 380 mm size that is reinforced stone concrete. As per NSCP, it has 23.6 kilonewtons over cube meters. Multiplied with the size, and the answer will be 2.69 kilonewtons per meter. Last is the parapet wall on the roof. The thickness is also 150 mm CHP that is fully grouted using 19.6 kilonewtons per cubic meter density of unit and plastered on both sides with 300 mm high. The answer is 0.99 kilonewtons per meter. This is the dead load of 5th floor. Copy the previous computation and add the necessary finishes. This one is for the 4th floor to 2nd floor. We assumed an additional 40% for the total weight of the slab and the answer will be 6.398 kPa. The following are live load computations. This one for computation of the distributed load for dead load. Next is distributed load from roof slab to roof beam. And last but not the least is the distribution of load from roof beam to fifth floor columns. The answers are 46.19 kilonewtons and 54.79 kilonewtons. Next is the lateral load analysis. Following the NSCP, we've listed the following required variables to analyze the seismic loads for the building. The first step is determining the total weight and height of the structure, as these directly influence the earthquake forces. We also identify the specific environmental and structural factors that dictate how the building will react to a tremor or ground shaking, and define how the building is designed to resist these lateral forces. Using the listed parameters, we'll calculate the site-specific coefficients and structure period. Next, we determine the vertical force distribution to see how the total base shear of 3,335.44 kilonewtons is distributed across each floor. Since our calculated structure period is less than 0.7 seconds, we set the concentrated top force to 0, meaning the entire seismic load is distributed solely based on the height and weight of each level. We applied the designated formula to each floor, resulting in lateral forces ranging from 235.594 kilonewtons at the first level to 979.49 kilonewtons at the roof. Lastly, we illustrated these story forces in a diagram to visualize how the building will be pushed laterally during earthquake events. For the next step, we determined the horizontal force distribution for the ground floor by calculating the column rigidities and identifying that the center of mass and the center of rigidity perfectly aligned, resulting in zero natural eccentricity. To account for plant irregularity requirements, we introduced an accidental torsion of 5% of the building dimension, as required by the NSCP, which we used to calculate the additional torsional shear for each frame. We continued these steps for the rest of the floor levels. These steps prove that no torsional irregularities exist in the structure. For wind load analysis, we still base for determining the velocity pressure at the mean roof height is 4.69 kPa based on the basic wind speed of 75 meters per second. We then calculate the design pressures for different building surfaces, finding the windward wall, leeward wall, and roof face suction forces, leading to the values written in the solution. To determine the wind load, we first calculate the floor area to find that each of the 5 levels experiences a uniform force of 858 kilonewtons. Since the total height is 15.4 meters, we apply the uniform vertical load distribution because the structure falls under the 20 meters threshold for this simplified method. The design considers 2 slab conditions. Case 3, a corner slab with 2 discontinuous edges. And Case 2, an interior slab with 1 discontinuous edge. Based on the final structural analysis, both cases require identical reinforcement detailing. This is the table we use as a reference for computation. The specified reinforcement consists of 12mm diameter bars spaced at 265mm on center, provided for both top and bottom reinforcement, ensuring adequate strength and uniform performance across different slab conditions. The computation for grade slabs is generally less complex compared to suspended slabs. However, load evaluation must still account for axial loads and actual soil-bearing pressure. Based on the design calculations, the required reinforcement for the grade slab consists of 10mm diameter bars spaced at 350mm both ways. This project utilizes 3 footing types: interior footings, side footings, and corner footings, with interior footings carrying the highest load. Using concrete unit weight of 24 kilonewtons per cubic meter and a soil-bearing capacity of 150 kilopascals, the total computed load of the structure is 47,385 kilonewtons. This load was distributed across 31 equivalent footing units, resulting in a footing reaction of 1,528.55 kilonewtons per unit. The required footing size is approximately 3.9 meters by 3.9 meters with a thickness of 0.3755 meters. And minimum reinforcement requirements resulted in 12 20mm bars for F1, 6 for F2, and 3 for F3. Column design follows the same interior, side, and corner classification, labeled as C1, C2, and C3. Based on calculations and code requirements, all columns are reinforced with 8 16mm diameter vertical bars and 10mm diameter lateral ties. For the beam design, the required reinforcement consists of 6 20mm diameter bars at the top, two 20mm diameter bars at the bottom, and 10mm diameter stirrups to resist shear and provide confinement. The structural system is designed not as a limitation, but as a framework that enables architectural beauty and spatial quality. Through a well-coordinated column grid and efficient beam slab system, the structure allows for wider spans that support open-plan residential units. This flexibility enables spaces to adapt to different users without excessive partitions, reinforcing the project's human-centered design. Strategically placed beams and columns make it possible to introduce light-filled corridors and breeze-block facades without compromising structural integrity. By transferring loads efficiently through the frame, the building accommodates visual openness, natural ventilation, and controlled privacy. Localized cantilevers and extended slab edges are structurally resolved through proper load distribution and reinforcement detailing. These elements enhance facade articulation and shading, strengthening the architectural expression while maintaining safety and performance. In this project, structure and architecture work as one system, where engineer precision supports light, space, and form, transforming technical necessity into an integral part of living experience. By prioritizing natural light and ventilation, minimizing reliance on artificial energy, and designing flexible and open-plan living spaces, Lux Vivere responds to the evolving needs of contemporary residents, from families, students, and to working professionals. The integration of base blocks, thoughtful orientation, and adaptable units reinforce the project's commitment to comfort, sustainability, and overall user well-being. Again, this is Rain Madel, and this has been a presentation of Lux Vivere, a proposed mid-rise development. Thank you for your time and attention.